All right. Looks like things are working. Ah, here comes Al. Good. Yeah, minimize this stuff if I can figure out how. There it is. All right. Good. There come a few people. Hi, Al. Good. Looks like things are working. I'll wait about a minute before we get going here. Well, I guess it's almost 6. Give me a minute to figure this out. My charger is not. Come on. Oh, I know what happened. All right. There we go. Okay. All right. So it's time to get going. I guess we've got as many as we're going to get. Others may come in later, but there's no need to wait for them. So we're down to chapter 7, which is very short. And after that, we'll do the little bit of starting chapter 8, which is long. So access control is, of course, restricting what people do to match your security policy. And you have to test to see how well this is working. And there are a lot of different kinds of tests. Penetration tests are where you get an outsider to hack into your company and find the vulnerabilities and then submit a report listing your vulnerabilities and how to improve your security posture. It's required by PCI compliance if you take, I think, more than 200,000 credit card payments a year. And a large number of people pay for 10 tests on a regular basis now. They test often your phone network and your wireless network and your internet, and they try to pick the locks and sneak into the building, and they even often try to fool the people with social engineering to discern all the failures of your security policies. Social engineering is the oldest and most powerful technique, been around long before computers, just tricking people into doing stupid things. It's very powerful and very hard to fix because these guys exploit humans' natural desire to help others or their fears and insecurities. You somehow get them off balance so they feel like they're in trouble, and you're offering them some way out of that by doing something they really shouldn't be doing, like letting you in someone's account or letting you in a room or something. Anyway, some tests give the attacker no knowledge, so they have to find it themselves the way outsiders would. Other people provide them with some information, and these are just different types of penetration tests. Their Metasploit is a common tool used to attack systems and exploit known vulnerabilities. There are also closed source tools that have even more vulnerabilities in them, including ones that are not yet published and patched. So there's quite a few stages of the pen test here. They plan, then they do reconnaissance, finding out about your network and your buildings and such. Then they do scanning of the network and enumeration of accounts. So they find out what shares are available, what login accounts are available, and so on. They often run vulnerability scanners to find known security flaws, and then they exploit systems and take things over, and then they write a report specifying all the security problems they found and explaining how important they all are and making recommendations to fix them. The pen testers operate under non-disclosure agreements because, of course, they are learning information that should be kept secret about ways to break into a company, especially since they probably won't all be patched. And that's confidential information, just like medical information a doctor has. Vulnerability scanning is typically done with an automated tool. Nessus is a a tool that has a free version and a pay version. OpenVAS is a fork of it that's completely free. And this, like many other scanners, it goes through a long list of the long subset of the CVE list and tries to test for each little vulnerability in every system that it appears to have found on the network. It's not extremely accurate. Vuln scanners in practice only find about half the vulnerabilities they're designed to find, but they are thorough in that they do try to travel to every link on the website and every IP address on the system and so on. You really have to back them up with intelligent manual human analysis of the vulnerabilities, because vulnerability scanners will miss vulnerabilities, and they will also report things as vulnerabilities that are not really vulnerabilities. So you have to go through their report and manually verify the findings. A security audit is an entirely different activity. This is where you just have a long checklist of things that are supposed to be done on this network, and you just check to make sure they've all been done. And typically what you're doing is you're meeting a standard. So it is not, a lot of people in the security community get angry about this. It's not really a measure of security. It's just a measure of legal compliance. The rules say you must have these 100 things, so just make sure you got them and check them off. It doesn't necessarily mean you have really mitigated all the risks. It just means you've met the letters of the regulations. And PCI DSS is one, HIPAA is another, FISMA is another. There's many different frameworks of security that you have to comply with if you're in certain industries. All right. So you can also have a security assessment that tries to analyze your overall policies, your administrative controls, whether you're controlling change management, what other tests you've been doing to decide how secure you are. You can have internal audits, and you should, where your own employees make some measurement to see if people are actually obeying the rules, if your technical controls are in fact succeeding in compelling people to obey the policy, or if people are subverting them. And then there are external audits where you pay external people to test things. They're expensive, but if you pay for good consultants, they often find things that your internal testers will not find. You do have to review logs. A lot of companies don't keep enough logs, and a lot of them collect logs and don't actually review them. And this, I think, is changing quite rapidly. As people move into SIEM systems and other forms of centralized logging, it is now getting to be very common that there really is a central security operations center on the network, and they really are gathering all these logs from the web servers, the antivirus, the routers and firewalls, and the applications and databases. It's all coming to a central point, and it's being scanned with some kind of system like Splunk is a very popular one. It's expensive, but very good. That's the one we're using primarily in my network security monitoring class. And people are looking there, testing to see if they're finding known problems on the network, and that's the goal here is that you should actually be able to tell if you're being hacked by measuring all this information. So centralized logging is essential for this. You won't really be able to do much. You have to check every machine one by one. Instead, you get all the logs gathered from a machine and forwarded by some system over the network to a central point. And one common way it's done is with syslog that just sends it over UDP 514. There are other ways to transfer logs around. And then once you've gathered all the logs, you probably want to retain them for a while. Most companies would retain them for at least 30 or 90 days just so they can analyze their own security issues. And you may be required by regulatory restrictions to keep them for longer, depending on what kind of business you're in. So they can be audited by third parties, and so third parties can investigate security breaches such as financial problems in a financial company. And software has to be tested. There are a lot of ways to do it. Your programmers might make errors, and your apps that you develop in-house don't have a vendor providing patches, so you have to review your own source code. There are various ways to do it. You can do static analysis, where you run a scanner on the source code to look for common problems. It can catch things like format string vulnerabilities in C, where you print something out but you forget to specify the format string, or buffer overflows where you read in input but you don't check for the length of the input before using it. These are things that a source code scanner can find pretty easily. And you can do dynamic analysis, where you run the code and try to detect errors while it's running by doing things like sending in random input, trying to trigger crashes. Pair programming is a popular technique in agile shops where two people have to work together programming, the idea being, hopefully, that with two eyes looking at it, they'll more often notice when they're making mistakes. So here we got static coding. Static testing you can do with things like lint, and dynamic testing you can do either with knowledge of the source code or without knowledge of the source code, where people try putting in data that will drive the code into all of its corner cases, or give it unexpected values like very large numbers, very small numbers, letters and numbers, special characters, code that's very, very long, just every possible condition that might lead to an error that you can think of. All right, and there's a traceability matrix is another way to do it, where you specify the customer requirements and match them to the testing plan, make sure you've tested them all. And synthetic transactions, where you simulate business activities, trying to make sure that the application will function under real business concerns for real business purposes. There's different levels of testing. Unit testing is where you take little components and test them until they work individually. This is the whole point of structured programming languages. So instead of writing a long, complicated program to do something, you break it into little functions and write each function separately and test it. Then there's installation testing and integration testing to see how software will combine with other systems. Regression testing, which tests your software after it has been modified to make sure that all the essential features are still working. And then acceptance testing, where you decide whether it meets the customer's requirements. Fuzzing I mentioned before. This was used to find spectacular vulnerabilities in Windows in the time of Vista, and is now considered essential for any hardware or software product that comes out to do fuzz testing, where you just send random data to it, usually over a network, if it's any kind of network-connected device, and you find out if it does something unexpected, like crash it or have unexpected results. This is a way to find errors even without knowing the details of the code. I see a chat message. Requirements or specifications? That sounds like that's from the previous slide. Back here, right? Yeah, it could be either way, I suppose. You have some customer that you're writing software, which could be an internal, external customer, and you're testing to make sure it meets whatever they need. I think it could be considered either requirements or specifications. I hope I understand that question correctly. All right. And then there's combinatorial testing, where you try combinations of inputs. That's what I was mentioning before. It's something that the smarter fuzzers will do. They try to make sure and drive the code into every corner. What if this number is too small and you choose a different option here? Because that's usually where the errors are made. Let's see, another chat statement is coming in. Specs are much more robust and detailed. Okay, good, thank you. All right, that's good, thank you. All right, and then there's misuse case, where you formally model an adversary misusing the application. This is what Microsoft does. They call it threat modeling. And Microsoft has been for years explaining their software development lifecycle, where they do try to consider secure development at many stages during the development of software. They're very proud of this. Many other people imitate them. And they didn't used to do fuzzing until after they started making Vista. And Laurent Gaffey found 2 blue screen of deaths in Vista by fuzzing for just 10 seconds and humiliated Microsoft very much and forced them to add fuzz testing. Before that, Microsoft was opposed to fuzz testing because fuzz testing is a random process. You're just sending randomly mutated packets and you never know when you're done. And they preferred to have things like automated code review where you run it through certain tests and then they're all done. They didn't like the messy random nature of fuzzing, but they were compelled by the external evidence of hackers to accept that you should also do this random fuzzing process, which will catch errors that the other processes missed. All right, so your testing may or may not reach the entire application, but it would be best if it does. So this is called test coverage analysis. How many of all the possible cases of inputs have you actually tested? All right, so when you're done, you have output from these tests, and then you have to, if you do find unexpected results, then you have to have the code analyzed and figure out how to deal with those unexpected results, which is, of course, difficult and often not done very well, and a very common situation, which we have seen happen to Microsoft, I think 3 times this year already, is where they have a security problem, so they make a patch, and the patch is defective, so they have to recall it or have another patch on the patch, and sometimes even a third patch on the second patch, because it's just very hard to fix problems without causing other problems in turn. All right, I got some cahoots about that stuff. And here they are. That is chapter 7. All right. And I appreciate the help because I've never done that kind of software development, so it's all just on a theoretical basis for me. And real developers can often add more insight. They've changed the music again. All right, see how many people I've got? 5. There could be as many as 4 people in here. KT is the one not in here yet. I think KT usually joins. Wait a few more seconds. Are you coming, KT? I'll wait another 5 seconds. Oh, there we are. All right, so everybody's here. Good, let's go ahead. Okay, 4 questions. All right, what process would ensure HIPAA compliance? Right, a security audit, comparing your security controls to what they should be. All right, what process goes over UDP 514? All right, that's a syslog, which is used for centralized logging, to move the logging data to one central point. All right, what process takes place after updating software? All right, that's called regression testing, where you just test a series of required functions to make sure they still work as they should. All right, and what's the process Microsoft highlights in their SDL? All right, and that's threat modeling. I see nobody got it here. Let me say a little more about it, because I talk about this a lot in my classes. Students often come to me in class and they raise issues like, how should I be encrypting my emails or something? And that's what I talk about. You have to do threat modeling where you say, what are you concerned about? Because a lot of people say they don't want to use something that the NSA can hack into. And I say, is the NSA really your threat model? If you're trying to hide your data from the NSA, you're in big trouble. And there's probably nothing you can do to stop them. The best thing you could possibly use would be PGP, which is what Edward Snowden used. But I wouldn't be too confident at that stopping them either. But realistically, unless you're a terrorist or something, you probably aren't really trying to hide from the NSA. You're probably trying to hide from criminals that want to steal your credit card and things like that. And that's a whole different threat model. So this is where I think Microsoft has a very good point, that you don't just try to block every possible security weakness. You figure out what you're really worried about, and you try to focus your attention on blocking the realistic threats that are actually being exploited. It's frustrating for vulnerability researchers. I've done a lot of this. We inform companies of a problem, but they don't care because that particular problem is not the one that is really causing them to lose money right now. And they're right, really, that you have to focus on the one that's really hurting you, not every possible little problem. Anyway, so I see Al's the winner, which I think I've seen before. And let's go on to the next section, which I think that's it for this chapter. Yeah, and all I want to do is maybe the first section out of the next one, because that was only 25 slides, and we can do a little more, and it'll save us some time next time, because this one's pretty long. So this is one of the security operations topics. There are some redundant topics in the CISSP, which you see come over in a couple of chapters over and over, which is not bad, but don't be too surprised when you see things that you've already seen before. So administrative security procedures, these are policies you have to try to limit the risks from the way you treat people. These are general principles. Least privilege is a big one. This was Microsoft's big step forward with Vista and user account control. In Windows XP and earlier products, people typically logged in as administrator all the time, and they'd surf the web, and every time they went to a website and it tried to install something on their machine, it would just go right on. And it was after Vista that they finally were able to do this least privilege thing, where you are running without administrative access most of the time, and you only elevate briefly to administrator when you have to. And that should pass all the way through the company. Your telephone operators should not have access to the payroll systems, and so on. They should not be able to get to some part of the computer system they don't need, that can only get them in trouble, or some physical part of the physical building they don't need to get to. Then there's need to know, which is compartmentalizing information so that people are not able to get information, not necessarily that they don't trust them enough to know that type of information, but they don't need it for their job, so it's an unnecessary risk for them to have it. Separation of duties. A good example I've seen in CISSP books about this is the movie theater. If you go to the movie theater, you go first to a person with a cash register, and you give them money or a credit card, and they give you a ticket. And before you go to the movie, you have to hand that ticket to another person who stands there ripping the tickets in half and letting you in. Now that is separation of duties. They don't do that because they want to pay two people. They do it because people working at the movie theater will just let their friends in for free. And this way, they can't, because they have to pass two different people. So only if those two people would both agree to cheat their boss and let somebody in would they be able to do that. And that's the point of separation of duties, whereas one person does something and another person also has to sign off on it before it takes the dangerous effect. Yeah, I hear a chat comment coming in. See if I can get it on my screen. There we go. A student at ISU took us for $116,000 due to a lack of this control. Wow. But they paid you back. Yeah, that reminds me, when I was in Illinois at a different campus than the one I was at in Chicago, the alumni fund director spent something like $5 million on like mink coats and cars he gave to prostitutes and stuff. And he was signing them on official college alumni checks that were supposed to have two signatures. And the bank just took them with one signature. So the college was able to sue the bank to get the money back because it was supposed to have a second control and the bank just ignored it. But yeah, it's certainly, that's the problem. If you have one person who can spend money without another person having to countersign, then they can really rip you off. Of course, collusion is possible. One of the cases I worked on when I worked at an escrow agency involved a gigantic collusion. These people stole more than $2 billion from supermarket chains in America, and they had 10 people responsible for shipping at major supermarket outlets and people responsible for trucking. And they were just forging documents saying that whole truckloads of stuff had come in and then claiming it had arrived when it didn't arrive and pocketing the money from it. And it went on for years, and they stole an enormous amount of money before they got caught. So, just the fact that people will have to collude to do it, it doesn't prevent it, but it makes it more difficult. Anyway, rotation of duties and job rotation and mandatory vacation are all very good, because another thing that tends to happen is you have somebody who finds a way to cheat your system. Like they find a way to take money from a fund and then falsify the document so it isn't obvious how the money vanished. And because this is often when a person will not take a vacation, this is why they won't take a vacation, because they're doing something fishy. And forcing them to take a vacation or rotate to another job and have someone else take over will expose the fact that they haven't actually been correctly filling out the various controls. So that's why that's often a case. Non-disclosure agreements, I mentioned before, I make my students sign these when we do penetration tests and security audits of companies, which we do. You do have to keep things private when you find problems. And background checks are very useful. The simplest background check of all, where you just take someone's resume and you actually call their previous employers to see what they have to say about them. I think 75% of the time companies don't bother doing that. And of course, very often the new employees steal from the company, and they also stole from the last company. You would have found out if you'd just done the most elementary attempt to check their background. All right, let's see if there we are. Privilege monitoring is very important. One thing that happens a lot at companies is they have administrators and there is nobody watching what the administrators do. They're just being trusted, and they often do foolish things. I think Pacific Bell here for years had an internal server all full of stolen intellectual property like movies and music that the network administrators were trading back and forth using company resources and implicating the company in the crime, and nobody knew. So you want to have someone in your administrative oversight looking at some list to see what has the administrator been doing, how many administrator accounts are there, how many new accounts are created, how many copies are being made of data, and things like that, to see if the accounts with privileges are doing unreasonable things. Forensics is the general activity of reviewing the activity on a machine to find out what's been happening here when something bad has happened. The original case here was crime, where you have a crime of some sort, and now you're going to gather the evidence from computers to prosecute people. These days, incident response has gone quite a bit beyond this, but we'll get to that a little later. Anyway, anti-forensics are things that hide the forensic evidence. There's quite a lot of ways to do this. One way is to have memory resonant malware so it never puts any files on the hard disk. This stops the old-fashioned forensic system, which primarily consisted of making an image of a hard disk. In fact, until maybe 5 or 8 years ago, the typical rule was you go to find a computer and you unplug the plug to just turn it off abruptly, and then you image the hard drive, and that's your forensic evidence. Now, we don't do that anymore because you really want the evidence that's in RAM. Now, the evidence in RAM is usually not much use to convict somebody because files in RAM don't have creation dates or owners, but it does help you understand what's going on with things like malware infection, which is often more important in a corporate environment than prosecuting people. So first you identify the evidence, then you acquire the evidence. It means you make a copy of it someplace so it can be preserved and analyzed later. You do not analyze a system by just typing away on some suspect system. This is an amateur move. You're corrupting the data while analyzing it. You make a image of the system, and then you analyze the image, and then produce a report if you're planning to go to court. Most companies make the decision very early to not go to court because they don't want to bother with all the procedures of preserving evidence up to court standards. They just want to find out what's going on so they can fix it. And if they need to punish somebody, they can just fire them. They don't really need to be hauling them into court in most cases. So a live capture is where you run software on the machine you're taking an image of, so it has a small effect on the machine, and you just capture the evidence right off it while it's running. You can also make images of any kind of storage device, hard disks, cell phones, and so on. If you make a complete binary copy of every bit on the hard drive, you can recover the deleted files. This is much more complete than a normal backup. If you have a 500 gigabyte hard drive and you've got Windows installed, it might only be using 20 or 30 gigs. And if you made a normal backup for the purposes of restoring the system in case it goes down, it would just be 20 to 30 gigs. But a forensic image is always as big as the entire drive. If you have a 500 gig drive, the forensic image is 500 gigs. And it includes all the bits on the drive that are not currently in use. Those are called unallocated sectors, and those contain deleted files. And that's often where the most important evidence is for at least criminal activities that involve saving files on the disk, like browsing forbidden websites, which the criminal attempts to hide by later deleting things. So like I say, allocated space is normal files that are in use that have a file name and a creation date and an owner. Unallocated space either is completely empty because it really hasn't been used yet, but in most cases, what is left is there's leftover chunks of files that have been deleted but haven't been overwritten yet. And you can reconstruct those with forensic tools and often figure out what people have been doing. Then there's slack space, which is little fragments of files, less than 512 bytes typically, at the end of clusters. Not usually terribly valuable, but in principle, there might be some information there. And then there's bad blocks, clusters and sectors, which again are like those other ones. These contain some data that has some flaws. So usually not terribly useful to a forensic investigator, but more of a concern for a disk data remnants issue. Like if you want to be sure credit card numbers and passwords are not on there, it is a problem because it's usually not possible for you to erase the bad sectors, and yet you do not really know that the bad sectors don't include fragments of data. So you can make forensic copies with Norton Ghost or FTK Imager, a free product from the company that makes FTK, one of the main forensic suites. There's two famous commercial forensic suites, FTK and NCASE. Police departments mostly use NCASE, and corporations mostly use NCASE. The FBI uses FTK. Those are the two big giants in the game. You can also do network-based forensics, where you analyze network traffic to find out what's going on. One simple example of this is network intrusion detection systems that look at the network traffic and try to spot attacks in progress. The network forensic people take the network traffic and reconstruct emails and IM conversations and file transfers, and you can figure out what people have been doing. Even if they do something like erase the hard drives of machines they've used, if you've been recording the network traffic, you can still go back and reconstruct what happened. So there are ways to analyze software forensically. If you have malware samples, you can reverse engineer it with a variety of techniques. The most drastic technique is to use disassemblers to just look at the raw assembly code and read it. What's much more efficient and productive is typically to run the malware intentionally in a virtual machine and watch what it does. That's usually faster and simpler to find out what it's doing and how to clean it off. Reading through the assembly code is an advanced, difficult skill you only go to when the easier techniques fail. Embedded device forensics is growing rapidly. As people have portable devices like cell phones and SSD drives on their machine, you have to analyze them, and the physical structure is different than magnetic hard drives, so the tools are a little different, but the general principle is the same. Another big forensic-related field now is e-discovery. If you get sued for some reason, then you will get a court order, and this happened to Google and Oracle. Oracle sued Google, saying that when they made Android, Android is largely based on Java, and the apps on Android phones are written in Java. And Oracle, or Sun, I'm not sure if it was before or after Oracle bought Sun, sued Google and said, you should have paid us royalties for all that Java you put in Android, and they wanted some enormous amount of money, like $3 billion for it. And Google was then required to cough up evidence showing all their design decisions made about how they used Java in there. And there was one letter written by an engineer at Google which said, in the early stages of Android development, this guy said, wait a minute, we're using Java, and Java is a Sun product, and we are going to owe them royalties if we use this, so we shouldn't. And that letter went around the company to various people, but most of them put this paragraph on it, which you've probably seen in emails, that say, this is privileged attorney-client communication. The reason they put that on there is because that means you do not have to hand it over in case of a lawsuit. But one person removed that before emailing it, and the e-discovery company made a mistake, because you don't have to put it on every time you send an email. It just has to be on at least one, and then no copies of that email need to be produced. But they fouled up and sent that to Sun, and that nearly cost Google billions of dollars. Ultimately, they didn't lose the case, but they could have, just because of that. And anyway, that process is called e-discovery, and it's now, several of my students work in this now. It's a rapidly growing field of how to scan a computer network and gather all the evidence that must be submitted to the other side. And after you become a large enough company that you just accept that lawsuits are going to be a regular business problem, then you preemptively put indexing software on your network, which keeps track of everything, so it will be easy to produce all the relevant documents when you get sued. This is, by the way, one large reason that Microsoft Office, when they came to 2008, switched from their proprietary doc and XLS formats to docx and XLSX, because when companies were getting sued, it was very difficult for them to find all the spreadsheets and documents they had written about a topic because they weren't stored in a plain text format, and now they are. Now they're stored in just plain XML, plain text. So if you have something like a brand name or a person's name, you can just scan for that word through all your Microsoft Office documents and easily find them. Anyway, all right, then there's incident response, which is another new field that's emerged out of forensics, which is where you are not trying to get evidence to lock somebody in prison. You are trying to deal with a security incident like getting hacked from the outside. Most corporations, if they get hacked from the outside, do not really care who did it or care about tracking them down or locking them up, because that's difficult and wouldn't really accomplish anything. All they really want to do is find out what they did, fix it, kick them out, and stop them from coming back. So here's the general stages. You prepare for incident response. You have a detection phase where you find out that some kind of security problem has occurred. Then you have containment, where you stop the damage from growing. You put out the fire so things aren't getting any worse. Then you have mitigation, where you kick out the bad guys and fix the problems so they can't get back in. Then you have reporting on this. And then you have recovery, which fixes, I think that's the part focused on fixing problems so the next person can't come in the same way. And then remediation and lessons learned. We'll go through these in more detail. So in preparing for incident response, you have training, you have policies written for incident response, you have a staff, an incident response team that is formed, and you provide them with enough equipment to analyze information on the network. You have a checklist. So first you have to have detection and analysis, where you determine if a security incident has occurred, and then you have containment, eradication, and recovery, where you find the problem, stop it from getting worse, kick it out, and then restore the systems back to an operational condition. And then you have a follow-up report at the end where you analyze, how did we handle this problem? How well did we do it? How are we going to improve our incident response performance to better handle the next problem? So detection is the first thing of just declaring an incident. There's always a lot of problems at a company. Things are breaking and things are going wrong. And not all of these are security incidents. You have to declare a security breach has really occurred here. And this, you have to decide whether this problem really represents a big problem, which we must now analyze with incident response, or just a normal routine problem that we just fix with tech support. So the response is containment, trying to stop the damage from growing further. So if it's something like a malware infection, you want to take all the infected machines off the network, to isolate them from traffic. You could power them off, although that is not usually recommended because you'd lose the evidence from RAM. All you usually do is disconnect them from the network, so you can still get evidence from them. All right, and I see another comment came through here, bragged about it. 60% of applications are rejected by checking their social media site comments. Yes, yes. Oh, that's right. It must have been back on the personnel stuff. Sorry, I didn't see that earlier to mention it. All right. Anyway, so mitigation is eradication, where you find the cause of the incident and clean up the system. And then reporting, as soon as you have malicious activity, you have to file various kinds of reports. There are technical reports going to the technical people in your company that inform them about the problem and get assistance from them as needed. And then there should be non-technical reports going to people like upper management, human resources, a legal team that explain what's happened and how bad it is without a lot of technical gobbledygook. Then there's recovery, where you restore the affected systems back to normal operations, and then you monitor them to see if the attacker returns. And then there's remediation, where you remove the vulnerability that permitted the incident and improve your security posture so that they can't come back in this same way again. And you have to have a post-mortem. This is something companies will tend to skip because they're just racing from one disaster to another, but that's an immature way to handle security problems. And as a company matures, they realize that you can't just pretend this is the only time we're going to get hacked. It's just going to be something that keeps happening. So we have to have a process whereby we go over what happens and improve it next time, because we can't, we're just going to have a professional, efficient, and ever improving ability to handle these problems, because they're just going to keep coming. And root cause analysis is very important. You have to really figure out how they got in. This, by the way, is extremely rare. I think 2/3 of companies never detect breaches at all. The only way they ever detect it is 18 months later, law enforcement officials come to them and tell them that they found their stolen data on some server. So they've been hacked for years before they even know. This is why my students were talking about the Uber breach. Uber was breached a year ago. A hacker stole a bunch of data, demanded a ransom. They paid the ransom and then just didn't tell anybody. And they're saying what rotten guys they are and they should be punished. And that might very well happen, because they probably broke data breach disclosure regulations. But realistically, from a viewpoint of a consumer, I don't think it really matters, because when we hear about a company that got breached, that lost our data, you can be guaranteed that probably 10 times as many companies you do business with also lost their data, and they don't even know. So, it's you certainly should not think, just because you haven't received a breach disclosure from people, that the companies you're doing business with have not been hacked. That is very naive. All right, so I got some cahoots about this stuff. This is chapter 8A. And we're here and here. All right. All right. All right. I think that's it. Yep, that's it. Okay. 6 questions. All right. So what's the process that gathers evidence for a lawsuit? Okay, that is discovery, and an electronic part of it's called e-discovery. All right. Which control is called compartmentalization? Okay, need to know. Nobody got it right, but that's what it is, keeping things in their compartment. All right, which control requires personnel to keep secrets? Non-disclosure agreement, good. All right, which process includes writing incident response policies? All right, that's preparation for incident response. You have to start by having a policy. All right, which process must include a non-technical explanation? All right, that's reporting. Good. Non-technical reports that people can understand are very important, both to succeed and also to keep people funding your incident response team, because they actually understand what good it did them. All right. And so which process includes submitting a final report to management? And that's the postmortem. You have reports at earlier stages, like how's it going and what damage was done and what do we have to tell the regulatory agencies. And then you should have a postmortem where you say, all right, how are we going to improve for next time? And that would include your final report summarizing the whole thing. And your management should be forcing you to do all those things if they're doing their job properly. Just like a couple of classes ago, we were talking about Equifax. They got hacked, and then some managers tried to say, well, you know, some technical guy just didn't put on a patch. And that's not really good enough, because management ought to be making sure that that stuff gets done. And if a technical guy doesn't do it, that's not the whole picture. That means they were wrong, but where was management? It was their duty to make sure that somebody did it. Anyway, all right. I don't think there's any point going on. I think that's taken the first section of this way, and we can do the rest next time. Are there any questions or anything? Well, I guess I'll stop it here. We'll do this again next week. Have a good week. I'm going to wait a minute for any comments. Hi, KT. Thank you. You're welcome. And I'll just shut this down. Okay. I'll put up the video later tonight. Farewell. End meeting. Okay.